Hello and greetings from UB. On behalf of the Office of Alumni Engagement and the UB School of Management, we are delighted you are able to join us for today's webinar presentation. My name is Christy Fields and I'm the Director of Alumni Lifelong Engagement here at UB. And I'm also joined by my wonderful colleague, Joy Rona. We are both so grateful you are able to join us today, and I hope you and your family are staying well. Since 1923, the UB School of Management has been developing leaders and making an impact on individuals, businesses, and communities around the world. In their mission to define the future of management, Dean Iyer has unified the school around 4 distinct areas of focus: business analytics, social impact of management, business of climate change, and innovation, entrepreneurship, and leadership. Each of these initiatives are helping to realize their vision of a world of transformational leaders and organizations who change society for the better. With that said, we are excited to welcome today's featured presenter, Dr. Mike M. Way. Dr. Way is an Associate Professor of Operations Management in the School of Management at the University of Buffalo. He received his BBA degree in Information Management and Information Systems from Fudan University, an MS degree in Industrial Engineering and Operations Research from Penn State University, and a PhD degree in Operations and Manufacturing Management from Washington University in St. Louis. His research focuses on supply chain management, dynamic pricing, strategic consumer behavior, and high-dimensional machine learning. His work has been published in leading operations management journals and machine learning conferences such as Management Science Productions and Operations Management and ICML. He has consulted in consumer electronics, financial, and IT industries. In today's session, Dr. Way will share how you apply various state-of-the-art machine learning algorithms, such as Lasso, MCP, and random projection, to tackle these challenges and demonstrate their effectiveness in real-life applications, such as the recommendation system and the assortment optimization system. We will leave some time during today's webinar for Q&A. If you have any questions during the presentation, go ahead and submit them. You'll see a questions section on your screen, and you can chat those questions to us at any time. And we will be recording today's session, and we'll send you all a copy within the next 24 hours. And now it is my pleasure to turn it over to our featured presenter, Dr. Mike M. Way. Welcome, Dr. Way.
Thanks, Christy. Thank you for the introduction. And also I want to thank the Kathleen, Joy, and Christy for inviting me to share my research with the UB alumni community. And as Christy introduced, my name is Mike Mincheng Wei. I'm an associate professor of the operations management department, and my research focuses on supply chain management, dynamic pricing, strategic consumer behavior, and high-dimensional machine learning algorithms. Today, I'm going to share my work related to the last research interest on high-dimensional machine learning algorithms. Okay, to understand what is the online learning and decision-making problem, let's first look at the hypothetical. Search advertising at Google as a motivation example. Let's suppose Kate wanted to check whether there are any deals for the upcoming Memorial Day holidays. So she typed the search keywords Memorial Day sales into the Google search bar. As Kate used her credential to log into the Google, the moment when Kate clicked the Google search button, not only Google server receives the keywords Memorial Day sales, but also Kate's personal information. For example, as Kate provided her name, gender, age information when she created her Google account, these pieces of information were known to Google. Also, as YouTube is also owned by the Google, the fact that Kate has subscribed to several fashion channels and YouTubes are going to be unknown information to Google as well. If the Kate uses the Google News, more information is going to be available for Google. And what's more, if Kate actually used the buy on Google to purchase a pair of the Michael Kors shoes and spend, let's say, $448 on fashion-related product last month, then all these pieces of information will be collected and fit into the Google's machine learning algorithms to provide a personalized advertisement that generates the highest expected revenue for Google. So we can say that each line of those description is going to be a piece of information or a single dimension of information, which we often call as covariate. And that information are going to help us to categorize Kate's profile and help us to predict her preferences. And when we combine all those information, we not only have one dimension, two dimensions, we have multi-dimensional information that gives a comprehensive categorizations on Kate. Now, how many dimensions are we talking about? We're talking about tens of thousands. We talk about millions. In some cases, we even talk about billions of dimensions. And all those information, or based on the high dimensional information, Google can guess that the Michael Kors, maybe Michael Kors' new designer bag may attract Kate the most. And therefore, we're going to display this ads to Kate. And upon observing this Michael Kors' advertisement, the Kate may like this recommendation and actually click to purchase this bag, and which time the Google are going to generate a revenue. And this fact that the Kate actually clicked their advertisement send a positive signal to the machine learning algorithm at Google, suggesting that current algorithm works quite well for Kate, and therefore Google should continue using the current algorithm to recommend future advertisement for Kate. Note that even if Kate does not like this advertisement and choose not to click this advertisement, such a low non-clicking behavior is actually helpful as well, because this also would send a signal, this time negative signal to Google by saying that, look, the current machine learning algorithm does not work, so please revise your algorithm to improve your prediction accuracy and recommend a better advertisement next time. This is not only unique to Kate, at the same time, maybe another user, say Max, also search the bandit algorithm on Google based on the multi-dimensional covariates associated with Max. This time it's going to be different from Kate's covariates. The Google can recommend a different advertisement. In this time, it's a textbook. In reality, there are not going to be one Kate, one Max. We talk about thousands of Kate and Max who are searching simultaneously on Google, and then clicking or non-clicking behavior will continuously teach and help train the machine learning algorithm to provide a more accurate, personalized advertisement based on each user's individual high-dimensional covariates and characterize this specific user. All right. However, the search engine's ability to accurately learn and predict consumers' preferences, or we say that click-through rate, is often crimped by the high-dimensional search advertisement data coupled with a limited sample in terms of users clicking or non-clicking decisions. Counting, let's say, more than 750,000 distinct words and the combinations, there's nearly infinite possible queries or combinations that the user can submit to Google or any search engine to get a response. For example, in 2023, Google answered 1.275 billion unique queries every day. And it has been estimated that 16 to 20% of the queries submitted every day never have been used before. So those can be new queries which have never been used. Hence, to accurately estimate those single advertisements click-through rate based on those queries, the search engine must require billions, if not trillions, of samples in which the customer either click or not click on this ad. And this craving for samples will be further intensified if the search engine practices personalized advertisement by taking into consideration of individuals' information, such as your demographic information, geographic information, browsing history, purchasing history, all those information taken into consideration. then the high-dimensional data is even going to grow even further. But at the same time, the available samples for the search engine to learn and predict the click-through rate are greatly limited. It has been suggested that idealness to run a new marketing campaign promoting a sales event or merchandise is around 45 days, during which time the average advertisement is expected to reach approximately 1/3 of a million of the users. In the nutshell, we're talking about using less than a million of samples at the most to train the machine learning algorithm to learn billions of high-dimensional covariates. What more is that among those 1/3 of a million users, a very small portion can be selected to perform costly experiments to learn the click-through rate. And that number is even smaller compared to the size of the billions of queries of individual data. And the high-dimensional data with a limited sample problem is not unique only in the personalized search advertising industry. It's essentially everywhere. For example, when we try to recommend a news or promote products during a flash sale event, then the life cycle for the product or for the news is extremely short, typically in terms of hours. Then how to learn consumers' preferences and responses based on billions of covariates characterize these users in such short time horizon is even more challenging than those 45 days marketing campaign we discussed before. Another example is the clinical trial. The covariates that characterize the patients, including demographic information, medical history, biometrics, genetic information, etc. Those covariates are in tens of thousands or in millions, and therefore high-dimensional as well. Yet in the clinical trial, the total number of patients, if we combine the phase 1 to phase 3, we are talking about a few hundreds to a few thousands, the maximum, which are much lower than the covariance dimension. So what's the problem with the high-dimensional features with limited samples? When we're facing this problem, then traditional method, for example, the OLS, the ordinary least square method, will have extremely high variance and result in poor estimation. Another problem in business setting is the interpretability issue. We always try to tell the managers what is behind this observation and how we're going to improve our decisions. Therefore, one way we can do is we can include all the possible high-dimensional covariates in the model to predict the user's click-through rate. But not all the covariates will have the same impact on users' click-through rate or influence the user's choices. For example, maybe if the user have purchased the Michael Kors shoes before, then this user is highly likely to be interested in the Michael Kors bag. Therefore, when we try to capture this user's preferences, then we may use the fact that this user have purchased the Michael Kors shoes before. But at the same time, whether the user is currently using the Google Chrome browser or Microsoft's Edge browser to purchase or to browse in this website may have nothing to do with whether the user is going to click this advertisement or not. In that case, although we have that piece of information as well, but we shouldn't include such a covariant in the prediction model. Yet, the traditional methods such as ORS could not identify those significant covariates and exclude those unrelated covariates automatically. And leaving those uncorrelated covariates in a model makes us harder to see the effect of important covariates and harder to speak in the business terms of what is the main driver behind the consumer's behavior. Now, we have understood the challenges of the high-dimensional data with a limited sample on learning consumers' preferences. Now we try to turn our attention to how the decision maker is able to learn and make decisions to maximize the revenue performance. So again, let's try to use the personalized search advertisement example to understand how those machine learning algorithms behind the Google or any other search engine are able to recommend and update its advertisement by learning from the customer's clicking or not clicking behavior. In and of itself, the search engine search advertising occurs when an internet user searches certain keywords or queries in an online search engine. And then the search engine are going to collect both the queries information and the customers, users' personal information. And in response to those information, their search advertisement, the website is going to respond with two different search results. The first research result will be some of the sponsored advertisements, such as those advertisements are going to be sponsored. And those sponsored advertisement was calculated based on the search keywords and the user's personal information, try to generate this sponsored advertisement. And also at the same time, they're going to display some of the search results, which only based on the queries their customers input into the search bar. So the purpose, how the Google going to generate the revenue is when the customers clicked one of those advertisements, then the sponsor of those advertisements are going to pay a Google for each of these eyeballs shown to the customers. So the objective for the search engine was trying to maximize the number of customers who are going to click this advertisement, or in other words, try to maximize the probability of the clicking for the displayed ads, which is so-called the click-through rate. In order to make the advertisement display optimal to maximize the click-through rate, there are two different philosophies for the website in selecting which ads to recommend to the user. The first philosophy is called the explorer mutation, which means that the website could always display the advertisement that has the highest click-through rate and therefore generates the highest expected revenue. The idea behind this seems to be very intuitive. The objective is to maximize the expected revenue by maximizing the click-through rate. Therefore, therefore, we should always recommend the advertisement with the highest estimated click-through rate. And if the search engine already know the accurate click-through rate for each advertisement, then this exploitation method is actually optimal. Yet the problem is that the search engine does not have the accurate estimation of the click-through rate for each ad, especially at the beginning, or especially when the advertisement is new, have never showed to the user before. In that case, what would happen? Let me try to give you a concrete example to see why this method going to fail in practice. Again, let's use the microcourses back and the algorithmic learning theory book, for example. The search engine need to select one of those two advertisements for each arriving user. Suppose that the search engine, based on previous data and observations, estimate that the click-through rate for the bag is 50%, and for the book is 33%. So when the first user arrives, because the bag have a higher click-through rate than the book, therefore, by following the exploitation policy or philosophy, the search engine should recommend the bag to the first user. And upon observing this advertisement, the user are going to click or not. If, let's suppose, this user actually clicked the bag, then this one actually indicates the customer clicked the bag. Based on this information, the search engine are going to update the bag's click-through rate to be a little bit higher than 50%, because now one customer clicked, so the click-through rate may be higher than 50%. At the same time, because the book is not recommended to the user, therefore there's no additional data or sample collected for the book. So there will be no updating for the click-through rate for the book at this time. So when the second user comes, as the bag still have a higher click-through rate, the search engine will continue to recommend the bag. Yet this time, this user is not interested and choose not to click this advertisement, so the search engine will update its click-through rate back to 50%. And so on and so forth. When the third customer comes, we still recommend the bags because it's a high click-through rate, so on and so forth. And as you can see, by the end of the time, we actually observe lots of samples who either clicked or not click the bag advertisements. Therefore, based on those information, we can accurately estimate what will be the true click-through rate for the bag. In this case, we can calculate that the actual click-through rate is actually 50%, which is consistent with our early estimation. But at the same time, as we never recommended the book advertisement, so there's no additional sample collected for the book advertisement. So we may never be able to learn the true click-through rate for the book ad. Well, and what if the previous estimation for the book's click-through rate is wrong? The true click-through rate is actually 66% instead of 33%. That means the bag advertisements we are going to keep recommending is suboptimal. And we should have recommended the book to max our click-through rate and maximize our revenue. Yet we will never be able to correct our mistakes because under the exploitation policy, we will never able to collect the samples for the books to correct the estimation mistakes and learn the true click-through rate for the book advertisement. Hence, at this time, the pure exploration policy is suboptimal or not optimal. So there comes the second type of recommendation policy. It's called the exploration policy, which means that the website should always randomly display an advertisement to collect enough samples for each advertisement so that we are able to learn the true click-through rate as time goes by. Then the question we want to ask is this exploration policy optimal? Let's look at the same examples. Again, the books and the bags click-through rate for the early estimation is 50% for the bag, 33% for the book. And when the first users arrives, now the website does not choose to recommend the ad based on the estimated click-through rate, but to randomly select and recommend an advertisement. In this case, it's going to recommend the book. And the user are going to click this book because the user going to like it. Therefore, we're going to update the click-through rate for the books to a higher number. And when the second users arrives, we're not going to base on the click-through rate to make the recommendation. Instead, we're going to use the randomize between those two. So this time, we may recommend the bag, and the customer also clicked, so on and so forth. So for each customers, then we are going to randomly select between those two, make recommendations, and observe how the customers are going to respond. So if that is the case, in the previous example, we are able to learn the actual click-through rate should be 66%, so we can correct the previous examples' mistakes. But what happens is this time, the estimation for the bags and for the books is accurate. So what does it mean? That means every time we recommended the book advertisement, we have made a mistake. Because the book advertisement has a high click-through rate, we should have been recommending the bag advertisement to the user every time to maximize the click-through rate. So in this case, the exploration policy also going to fail. Hence, either the exploration policy or the exploitation policy alone will not work. And the exploitation policy aims to maximize the click-through rate, but ignore the learning. The exploration policy focuses on learning, but fails to maximize the click-through rate. Hence, we need to balance between those two policies. So let me try to first quickly go through the model analysis and proofs. I don't think we have time to go through the details, but let's try to give you the overall idea. The first idea we try to do is we will first try to understand how the covariates are going to have impact on the customer's learning and prediction accuracy. Let's say we have the high dimensional feature vector that includes all the available information to the decision maker. For example, if I want to purchase a bag of potato chips from, let's say, Walmart or Amazon or any store, then there are many covariates available, such as the color of the packages, the brand of the potato chips, the size of the potato chips, but also we have other information such as who is the operator who sells the package during the production procedure, and where is the warehouse last stored this bag of chips. All those information are available for decision maker, but not all those available information are equally valuable to predict the user's utility and choices. For example, in this case, I think maybe the color of the package, the brand of the package of the potato chips, the size of the potato chips may have a higher impact on whether the customer is going to choose this potato chips or not choose. But those information, such as operator sales the package and warehouse for the storage, may have no impact at all. Therefore, the impact of those covariates on the customer's utility is going to be larger for those significant features, but going to be zero for those non-significant features. So one of the important benefits of using the machine learning algorithm was trying to identify which features are actually significant, because those significant features are unknown at the beginning. So we need to learn and using those information to make a prediction. Then we are going to use the so-called the Lasso and MCP algorithm to try to run this algorithm to identify which are the significant features. And therefore, by identifying those significant features, we are able to reduce this high dimension problem into a considerably low dimension problem. That means by filtering out all those features, maybe millions or billions of features, we may end up with thousands or 10,000s of available valuable features for us to predict the customer's predictions or choices. So that is the first step. The second step, one problem with those algorithms is solving this Lasso and MCP problem is very complicated, because it's going to be non-linear and non-convex problems. It's take time and effort to solve. Sometimes it's not solvable. So we propose a two-step weighted Lasso procedure to solve this MCP problem. And each step is going to involve in convex optimization, which can be solved in a reasonable period of time. And also, we're going to propose a so-called epsilon decay randomly sampling method, try to balance the exploitation and the exploration. This algorithm, the decision maker were going to choose to draw a random sample for each arriving customers with decreasing probability, to randomly select the decisions from decision set with equal probability to do exploration. But as time goes by, the probability for you to choose to do a random sampling is going to reduce, and therefore you are more and more going to maximize your exploitation by choosing the advertisement, maximize your revenue, instead of trying to learn what will be the true click-through rate. So this epsilon decay random sampling method can balance the exploitation and exploration trade-off, because we're not going to explore too much to significantly sacrifice our revenue performance, because the number of random samples we try to generate is going to decrease in time. But at the same time, we should have sufficient random samples to guarantee the quality of the learning and the quality of decision parameters estimation. And this is how this algorithm is going to work. Instead of looking at those mathematical equations, let me try to give you a general idea of how we're going to perform this algorithm in practice. So we're going to look at each customer. So when each customer arrives, then we're going to run random sample, a total coin. And the probability for the coin to land the head is going to decrease as time goes on. But if this coin actually lands on head, then we are going to do a random sample method. That means we are going to randomly select the advertisement for the total pool of thousands of the advertisements, and then recommend a random advertisement to the customers or to the users to learn what is the customer's click-through rate for this advertisement. Therefore, as time goes by, if we have multiple customers come in, then we should be able to learn all the arms click-through rate. And what if the coin lands on the tail? Then in this case, we're not going to randomly select the arm. Instead, we're trying to do the exploitation, try to maximize our revenue performance. To do so, we're going to use a two-step procedure to determine the optimal advertisement we should recommend to the customers. The first, we're going to use only the samples collected from the random sample set to have a rough estimation of which advertisement is supposed to have the best possibility for this customer to choose from. In this case, we may have multiple advertisements, maybe 10 advertisements come out to this shortlist. Then we're going to use all the samples collected, whether it's going to be collected by using the random sampling method or the profit maximization method. Then we're going to use all this data to do a more precise estimation and try to identify the final advertisement we try to recommend to the customers. And when each customer comes, we're going to go through these steps, so on and so forth. And this is how the GMCP bandit algorithm works. At first, we're able to show some theoretical results, try to see how this algorithm compared to the best case scenario and the worst case scenario. And we can show that on the covariance dimension, the expected cumulative regret is going to be upper bounded by the log t. That means the worst case, in the worst case scenario, the regret is not going to increase more than log t. This is the best case. This is actually the state-of-the-art algorithm, which has the lowest regret compared to any policies in the theory. Because traditionally in the literature, the bandit algorithm have polynomial or polylogarithmic bounds, and this is the lowest bound we can get. In addition, when we talk about the sample size dimension, the expected regret is also upper bounded by log t. And this, as you can see, this is going to be the upper bound, the worst case scenario. And in the literature, Goldenslug and Zivi in 2013 says that for all the possible algorithms which have invented or not invented, the best case, you are not able to get better than log t as well. So we can get log t, so our upper bound actually matches the theory's lower bound. That means this is the best algorithm. In theory, you are able to propose in order to maximize your revenue or minimize your regret. Okay, as you can see, this is you may say this is just a theory. Can you show me some of the practice? So in the last two slides, I'm going to show two applications to you. One is in the healthcare industry. In this healthcare industry, we're talking about the optimal warfarin dosing decisions. I'm not expert in the healthcare, but to my understanding, the warfarin is kind of medicine you inject into the patients, try to reduce the risk of heart attack. And typically there's three levels of dosage: the low level, the medium level, and the high level. And in this data set, we are able to collect about 5,000 patients' data, and there's going to be 93 covariates going to capture each individual patients, including demographic, diagnosis, genetic information, try to predict what will be the optimal warfarin dosage we should inject into the patient. And now let me try to give you the direct result. In this picture, we're going to see that the vertical bar is going to be the percentage of optimal dosing decision. The higher, the better. The horizontal is going to be the number of patients. And as we can see that if we are following the physician's decision, the physician also always follows the book's decision. The book always, or the industry always recommend the median level of dosage. So that means if the physician making decisions, the accuracy rate is about 54% always. And then we have this kind of oracle policy. That means that is the best policy you can ever get. And typically, there's no way you can get to that policy, because in order to get this oracle policy, you need to know everything about the patients. You need to know the right decision before you make this decision. So we use this oracle policy to represent the upper bound to gauge how much improvement, how much potential improvement there might be in the future for the future research. So we compared multiple algorithms, some of state-of-the-art algorithm, OFUL, Lasso bandit, OIS bandit, and our algorithm is the GMCP bandit, is this blue line. As you can see, as long as we have observed 40 customers dosing decisions, then our MCP bandit algorithms accuracy are going to exceed the physician's decisions. And we are going to reach about 62% of accuracy rate when we have 1,000 patients arrived. And that means by using the MCP bandit algorithm, when close, the accuracy bar or improve the percentage of optimal dosing decision by 70%, close the gap by 70% between the physician's decisions and the oracle decisions. Okay, let's look into the last experiments. It's going to be Tencent's search advertisement. This is similar to the Google's advertisement. You search your keywords into the Tencent's website, and Tencent are going to respond to advertisement to you. You can click or not click. Clicking going to give you revenue for the Tencent's website. So in this data set, we have more than 149 million sessions. And each session includes the user demographic information, queries issued by the user, advertisement information, users' responses, etc. And we have more than 500,000 of potential advertisement we can recommend to the user. And there's covariates. We have more than 26 million of unique queries, which each of them are going to be the unique covariates. We try to learn how the customer are going to respond to those covariates. And now this is the result. The horizontal line is going to be the number of users arrived at the website. The vertical line will be the average revenue generated by each users. So we try to generate as high the revenue as possible. And we have the random policy as the worst case scenario. That means for each arriving customer, I'm going to randomly select one of this 500,000 of the advertisement shown to the customers. That's called the random policy. It's pure exploration policy. And for those pure exploration, we can generate $2 for each customers. And also we have the oracle policy. That's the best policy possible. If we know, we can dig into the customer's head to understand which one do you like the best. If in that case, I can recommend the best policy. In that case, we can generate about $3.7 per each customers. Then we run our algorithms. We can see that our algorithm, the GMCP bandit algorithm, are going to generate a higher revenue than any other algorithm exists in the practice, as long as we have 20 customers. We observe 20 customers click or not click behaviors. So as long as we're 20 customers, we're going to have generating higher revenue compared to any other algorithms. And as time goes on, you have about 3,000 or 4,000 customers, then we can generate about $3.6 on average, which is going to be 10 cents less than the Oracle policy. So that's going to be, let's try to conclude. In this talk, I discussed the general MCP bandit algorithm, which have optimal dependence on sample size dimension and logarithmic dependence on the covariative dimension. And this algorithm actually warrants a better performance, both in theory and both empirically in practice, compared to the existing algorithms. And this algorithm can actually help to solve many online learning and decision-making problems in practice. As a matter of fact, we implement this algorithm in one of the leading e-commerce platforms, and we can see about 10 to 15% improvement in the click-through rate. All right, I think that is going to be end my talk, and I'm going to return the platform to Christy.
Excellent. Dr. Wei, thank you so much for taking time to share your knowledge, your expertise with us. Couldn't be more grateful for your time today. Before we go into a few closing remarks and whatnot, I do have a couple questions I just want to bring forth here. So, Dr. Wei, we hear a lot about AI. How does that relate to all of this?
Well, I think those algorithms actually are going to be the backbone supporting those AI, kind of the ChatGPT, all those things. So what we try to do is that we try to fine-tune those algorithms so that when we using the updated algorithms give to the ChatGPT or any other algorithms, those ChatGPT can evolve even further to give us more meaningful responses or help us to make decisions more accurately, or help the companies to even maximize their revenue in the future.
Great, thank you. You also, you mentioned, the website always displaying an ad that generates the highest revenue, and should the website always randomly display an ad to explore a user's response? Looking ahead to the future, with AI, as internets get smarter, what's the research say? How is this going to evolve over time?
Well, I think let's say 10 years ago, we're not cautious about our privacy. So we say that if you want data, take it. So Facebook, Google take tons of data, and then using those data to better understand you than yourself. And eventually, I think in the past 5 or 6 years, we eventually found out, no, we don't want to share all those information to the to those big corporations, because to be honest, sometimes I'm going to be addicted to some YouTubes or this TikToks, and it's going to waste lots of my time and efforts. So now I think the customers are getting more and more cautious about sharing or provide the permission for others to use the information to predict what I'm going to be like the best. And also this kind of the sharing the information can also help us to better understand each other. We're not going to live in an echo chamber anymore. So I think we still need the data, but we should be selective of which data we're going to use. And we should be careful of which data set we're going to use, trying to predict what will be the decision we're going to make. Whether we are going to make a decision based on advertisement, that's fine. But if we're using this decision to predict how or to swing public opinion, that will be very dangerous steps or directions I can see. But the thing is that I think each of us need to be the voice to speak out to those corporations by saying that, hey, I want to be the kind of decision maker for my own data, and you can take my certain information, such as geographic information, to recommend more precise local restaurant to me, but don't use my purchasing or browsing information to constrain my choice. And you think what is best for me, but actually that is going to much limit my decisions in the future. So I think this is going to be kind of the tug of the wars. The corporation always want to get more information, and think the government and also individuals need to be one step back, saying that my information belongs to me, and you shouldn't do that. It's not going to be necessarily a bad thing for the corporations as well, because we can see in my experience and the consulting experience with other companies, I do see that there's a limitation for how much we can improve by using those machine learning algorithms. So I think academically, we also need to step one step back to see, now, let's try to see, we have tons of information. Can we do a better decision by reducing those information from millions of dimensions to thousands of dimensions? If we can make a better decision by using limited information or thousands of information, then that will be even better. I think my research is kind of in that direction. Let's try to say, yes, you have millions of information or billions of information. Now, let's try to see whether we can shrink and we can strip away those uninformative information or those unrelated information. Therefore, those CEOs, those business managers can concentrate the time and efforts only on those small number of pieces of covariance or information to base on daily decisions on. So this is kind of the, I think it's going to be a trend. Before we want more information, so we collect more information. Nowadays, we say that let's try to see whether we can decrease the amount of information and focus on the quality of information for us to make better decisions. And I think we are at that tipping point. And I'm very proud that my research can contribute to that direction as well.
Very interesting, Dr. Wei. Excellent. Thank you for that thorough response. And I look forward to keeping in touch and seeing how this research progresses over time too. So thank you so much. Just on behalf of the Office of Alumni Engagement, the UB School of Management, again, very grateful for your time with us today. Dr. Wei, I'd like to turn it over to you for any closing remarks here, but I do also just want to remind everyone here with us that we have recorded today's session. You'll receive a copy within the next 24 hours, and you will also hear from us in additional webinars that are coming up over the coming weeks. But Dr. Wei, I'll turn it back to you for closing remarks before we conclude today's formal presentation.
All right, thanks. First, I also want to thank Christy, Joy, and the Office for the Alumni Engagement. This is a great opportunity to share the research with a large audience. And I have been doing this research for a long time. So if you have any ideas or you want to have collaborations, then please feel free to reach me either by email or stop my office if you happen to on the campus. All right, thank you, and thank you for coming.
Excellent. Thank you again, Dr. Wei. Thank you all for joining us today. Take care, stay well, enjoy the rest of your day, and we look forward to seeing you at a future event or on a future webinar. Thanks again, Dr. Wei.
Thank you.